So let's go ahead and talk a little bit more about limiting and access reactants. I know we've talked to you guys about limiting reactants, what they are and how we can calculate them, but we want to delve into this a little bit more and a little bit more with a systematic approach on how we want you to do these calculations, and then also considering what's your access reactant, how much access do you have left, and how do you determine all this? Just as a quick review, let's look back at some of the definitions we have. First, limiting reactant. Your limiting reactant is also known as your limiting reagent. We often call chemicals we buy reagents. So you can use the word reagent in place of reactant. More often than not, you're going to hear the word reactant in lecture, but in lab, it'll be a mix between reactant and reagents because we do call them reagents when we purchase them to do a reaction. The limiting reactant has two very important definitions. First, it is the reactant that is completely consumed or used up in a chemical reaction. Second, it will limit the amount of product that can be produced. Both of those definitions are vital to truly understanding what a limiting reactant is. The reactant in access, on the other hand, is any reactant that's in a quantity greater than is required to completely react with your limiting reactant. Now, some students may ask, why do we have a reactant in access? The truth is that there's a multitude of reasons why we may have a reactant in more than we actually need in a system. The reason reactions go forward we'll delve into a lot more, partly in Gen Chem 1, a lot in Gen Chem 2, and throughout your chemistry career here, regardless if you just go through Gen Chem, if you hit through organic or are going into higher level chemistry. You'll learn a little bit more about this every year. We learn a lot more about it in second semester. But there's always what we call a driving force. There's something causing a reaction to go forward. There's oftentimes it's related to your energy of your system. It's an energetically favorable thing for the reaction to do. Sometimes it's a desired product that the reaction would rather make. Sometimes it's creating more what we call disorder. You'll learn more about entropy in second semester. It's disorder or microstates of a system. We'll learn more about that in second semester. Maybe we gave the reactants energy and they need to dissipate that energy somehow. We heated them up or we shined a light on them, which gave them energy. In order to dissipate that energy, they undergo a reaction. All of these are possible reasons why a reaction may occur, and there's others as well. But when a reaction does occur, more often than not, at least one of the reactants is in access. One has to be limiting for one to be in access. You could have more than just two reactants, which means you could have more than one in access. Theoretical yield and actual yield also known as experimental yield. You guys covered in other videos, but again, just as a reminder, your theoretical yield is how much product could you theoretically make if you consume all of the limiting reactant and all of your limiting reactant actually makes your target product. Actual yield, I say actual because how much did you actually obtain. Better terminology for this would be your experimental yield. How much did you actually get out of the experiment? And of course, percent yield and atom economy. And those are all talked about in other videos. So just a quick review of limiting reactant and access reactants. Let's talk about a Chick-fil-A sandwich. If you have not been to Chick-fil-A, chances are you will visit it at some point during your fall semester. It's over in the Blue. It's a very popular place for students, and I think they use your meal swipes. I'm not positive on that, but I know my students have Chick-fil-A more often than they should first semester, and then they get kind of tired of it, but it's still always very, very busy. Chick-fil-A sandwiches contain a bun, which has 2 pieces of bread to it, 1 piece of chicken, and 2 pickles. I highly recommend checking out this sandwich. I'm a very picky eater. I don't eat pickles, so I order it without, but even as a picky eater, Chick-fil-A is very good if you like chicken. The recipe for a Chick-fil-A sandwich is 2 pieces of bread, hence your bun, 1 piece of chicken, and 2 pickle slices. So, if I had 8 pieces of bread, 5 pieces of chicken, and 10 pickle slices, how many sandwiches could I make? Well, most students look at this and can quickly tell me, okay, well, 8 pieces of bread, I could make 4 chicken sandwiches. With 5 pieces of bread, I could make 5 sandwiches. With 10 pickle slices, I could make 5 sandwiches. That means with these supplies, I could make a total of 4 sandwiches. That is completely correct. But what if we looked at this with stoichiometry? We can do this with stoichiometry. We can look at this as a chemical reaction. In this reaction, we would need a balanced chemical equation to be able to do the stoichiometry. So let's call our bread Br, our chicken CH, and our pickle slices PI. And we're trying to make one sandwich, which we're going to call SAND. This means I need 2 bread, 1 chicken, 2 pickles, and this produces 1 sandwich. Now, if I want to do this with stoichiometry, what I'm going to do here is I'm going to say, okay, I have 8 pieces of bread. How many sandwiches can I make? My number of sandwiches is equal to 8 bread times 1 sandwich for every 2 bread, because 1 sandwich contains 2. So 8 bread times 1 sandwich divided by 2 bread, that cancels out my bread, and that will give me 4 sandwiches. I can make 4 sandwiches with these supplies. So again, yes, we could do that faster because we understand how to put a sandwich together, but in the world of chemistry, a lot of these chemicals are hard to understand. It's hard to always correlate them. So we correlate by looking at moles to moles with stoichiometry. We can do this with stoichiometry as well. In this case, what is your limiting reactant or reactants? When I look at this, I can see that my bread is my limiting reactant because it limits me to making 4 sandwiches. What's my excess reactant or reactants, and how much excess is there? Well, I have chicken left over, specifically 1 piece, and I have pickles left over, specifically 2 pickles. How can I go ahead and apply this to the world of chemistry, though? We got to get out of the world of Chick-Fil-A and get into the world of chemistry, right? We're going to do reaction stoichiometry, and we're going to follow this system. If you follow these 6 steps, you will get to the right answer as long as your molar mass is correct and you're being careful, making sure you're using a balanced equation, and making sure that you're calculating things right in your calculator. This is a six-step process that you're going to have to learn, but the more you practice it, the more comfortable you'll be, and the more second nature it will be to do. I highly encourage you to practice a lot of these problems. They take time. They're not easy problems. We know they're not easy problems, but if you can get a really strong hold on this, you're going to be doing very well in this course, okay? A lot of students struggle with these concepts, so the more practice you can get now with this, the easier it will become for you. So what are the steps we're going to follow? Well, step 1, I want you to convert what you're given to moles. What do I mean by that? You're going to be given values for all of the reactants you have in the reaction. You're going to be given values in either volume, or atmospheres, or grams, or some type of measurement. Make sure to convert all of them to moles. We're not getting into gas laws in boot camp, but when you get into first semester, we're going to cover gases with you. You'll see then what I mean by pressure and stuff like that. Liters, you can often convert with density. So there's ways we can convert, but you need to always convert to moles. Step 2, ask yourself a question. If you use up all of one of the reactants, how much of the other reactant will you need? Step 3, answer this question using mole ratios. Step 4, ask a question. Do I have it? Do I have enough to complete what the answer is in step 3? Step 5, I want you to assign labels. I want you to say limiting and an excess. This is for your limiting reactant and your excess reactant. If you assign the labels to them on your paper, you are less likely to get confused and get them mixed up as you continue the calculations. Step 6, use a limiting reactant to solve the original stoichiometry problem. So let's go ahead and work an example. If you have 98 grams of B2O3 and 125 grams of HF, you combine these and allow them to react. The reaction produces BF3 and H2O. According to the given equation, now I do admit I did delete the equation from here because we want to go through and practice putting this reaction together for you guys. What is the limiting reactant? What is the access reactant? Now note, when it says what is, this is asking for the identity. Identity is a qualitative concept. It's asking me what is. It doesn't care how much of something I have. It just cares what it is. So on these, when it says what is, it's just asking for identity, not the value, not the amount, not the grams, not the moles, not the liters. But the next question says how much BF3 will be produced. That's quantitative. That's asking me how much. We're going to report these answers in grams unless otherwise noted. What mass of the access reactant will be left over? How much access reactant do you have left over? That is also quantitative, meaning you need to do a calculation. So first, let's go ahead and figure out our balanced equation. We know we've got B2O3 reacting with HF, and this is a solid, and this is aqueous. It is producing BF3 gas and H2O liquid. I need to balance this equation. And I know we're not focusing on balancing equations in boot camp, but it will come in fall semester. So if you get to learn and practice with it now, it just helps you coming in the with what's coming. The way I like to balance equations is I do what I call the counting atoms method. I write down on each side of the equation all of the individual elements or species that are present. And I make sure they match up. So I've got boron, oxygen, hydrogen, fluorine matching up here, so I can quickly compare them. So this is my reactant side. This is my product side. And now I'm going to add up what I have on each side of the reaction. On my reactant side, I've got 2 borons, 3 oxygens, 1 hydrogen, and 1 fluorine. Remember, when you see a little subscript after an element like this, or after a species, it goes to the element or species in front of it. When I look at the other side of the reaction, the product side, I see I have 1 boron, 3 fluorine, 2 hydrogen, and 1 oxygen. So I need to go ahead and balance this. The first thing I'm going to do is I'm going to multiply the boron on my product side by 2 to balance out my borons. Note when I do that, it changes my fluorines. I now have 6 fluorines present on my product side. So I'm going to multiply the fluorine on my reactant side by 6 as well. Now that has changed the number of hydrogens I have on my reactant side to 6. So now I'm going to balance out my hydrogens on my product side. If I put a 3 in front of that water, that gives me 6 hydrogens on each side. Notice that that also gave me my 3 oxygens on each side. Now my reaction is completely balanced. It's always a good thing to just check to make sure. So until you get real comfortable balancing out these reactions, I highly recommend you just go through and make sure that everything is balancing. So when I look at my reactant side, I've got 2 borons, 3 oxygens, 6 hydrogens, and 6 fluorines. Note that this coefficient out in front applies to the entire compound or molecule following it. When I look at the product side, same thing. This counts for the entire molecule or compound following it. So I've got 2 borons, 2 times 3, or 6 fluorines, 3 times 2, or 6 hydrogens, and 3 oxygens. My reaction is indeed balanced, and I can go ahead and move forward with the reaction. So the next thing I'm going to do is I'm going to start looking at the process that we discussed on the previous slide. First, I want to convert to moles. So step 1, convert to moles. I'm told that I'm starting with 98.0 grams of B2O3. Does that 0.0 really matter? Yeah, it does. It's our sig figs. It's our significance, our precision, and our measurement. 98.0. I do need to write down that 0. So I want to know the number of moles of B2O3. This equals 98.0 grams of B2O3. And to convert to moles, I'm going to determine the molar mass. You should always have a periodic table with you when you're doing calculations for this class. But just to help you guys out, in case you don't, boron's molar mass is 9.81 grams per mole. Oxygen, 16 grams per mole. Fluorine, 19 grams per mole. And hydrogen, 1.008 grams per mole. You guys can use that to determine the molar masses of all the other species. So to convert to moles, I'm going to multiply this by 1 mole of B2O3, and I add up the molar mass, and I find the molar mass to be 69.62 grams of B2O3. When I do this calculation, I find the answer to be 1.408 moles of B2O3. Note, I did keep an extra sig fig here just to make sure I don't mess up the calculation at all. I don't want to create round off error where it shouldn't be. I'm also going to do the same thing and convert to the number of moles of HF. I'm starting with 125 grams of HF. Convert that to moles of HF. And when I add up the molar mass of HF, I find it to be 20.01 grams of HF. When I calculate this out, I find this to be 6.247 moles of HF. Just like with the B2O3, I'm carrying 1 extra sig fig here. Now that I have the moles of each species, I want to move to step 2. Step 2 is, how much of one species do I need to completely react to the next? I want to ask, how much HF do I need to completely react (1.408 moles of B2O3? And do I have enough? How am I going to answer this question? With stoichiometry. Remember, stoichiometry is just a fancy word for mole-to-mole ratios. So, and I know I keep zooming and I apologize, I'm trying to figure out, I've got 1.408, keep my sig figs there, moles of B2O3. I want to know how many moles of HF will this take to completely react this. Based on my balanced equation, I see it takes 6 moles of HF to react 1 mole of B2O3. When I complete this calculation, I find I would need 8.448 moles of HF to completely react all of the B2O3. Step 4, ask yourself, do you have enough? On this one, you're asking, do you have enough HF? And the answer is no, you don't. What does that mean? That means you're ready for step 5 to identify your limiting reactant. And in case your access reactant. So limiting reactant here will be HF. How do I know that? Because to react all of the B2O3 I have, I would need 8.448 moles of HF, when in fact I only have 6.247 moles of HF present. So limiting reactant will be HF, and your access reactant will be B2O3. Now that we've identified which species is which, we can go ahead and use step 6 to answer questions. So, we know the identity of the limiting reactant. We've got that done. We know the identity of the access reactant. So, how much BF3 will be produced? We know that the HF is going to limit how much BF is produced. We also know from our balanced equation that 2 moles of BF3 are produced for every 6 moles of HF that are consumed. So step 6, use your limiting reactant to answer questions. I want to know how many grams of BF3 can I produce from my limiting reactant. I have 6.247, keeping track of my sig figs here, moles of HF. I know that 2 moles of BF3 will be produced for every 6 moles of HF. If I add up the molar mass of BF3, I find the molar mass of BF3 to be 67.81 grams to every 1 mole of BF3. And I apologize, there should be the word mole in here. When you calculate this out, you get 141.2 grams of BF3, but I know from my sig figs I need to round this to 141 grams of BF3. So this answers the question, how much BF3 will be produced? I can produce up to 141 grams of BF3. I want you to ask yourself at this point, does this answer make sense? Does it make sense that you would produce this much BF3? What do you guys think? The final mass here is higher than the initial mass of HF, right? We started with 125 grams of HF. I'm making 141 grams of BF3. Don't let that throw you off. Remember that BF3 is not HF. I'm using a portion of the HF to make that compound. It also has some of that B2O3 that's been added to it. The reason I pause there and ask that question is students oftentimes get mixed up on that when I ask that kind of question. They think, oh, the mass can't be bigger. The mass isn't bigger per se. It's just a different compound. So the last question I want to answer here is what mass of the excess reactant will be left over? So how much excess B2O3 do we have? Well, let's think about that. We know how many moles of HF we have. We know how many moles of B2O3 we have. We know we have more B2O3 than can actually react. So the way I'm going to do this is I'm going to figure out, well, how many moles of B2O3 do I actually need to react? So how many moles of B2O3 are needed to completely react the HF? If I've got 6.247 moles of HF, on my balanced equation I know that I have 1 mole of B2O3 reacting for every 6 moles of HF that are reacting. This gives me an answer of 1.041 moles of B2O3. I need 1.04 moles of B2O3 to completely react the HF. So if I need 1.04 moles of it, and I know that I have 1.408 moles in my reaction mixture, how much is left over? 1.408 moles minus 1.041 moles leaves me with 0.367 moles of B2O3 in excess. Now be careful when you do the subtraction here, because remember, we've been carrying 1 extra sig fig in our calculations to avoid round-off error. So technically, my sig figs are here and here. I need to be aware of that as I do this calculation. Since it's subtraction, I want to look for this number of sig figs with the least precision in my measurement, so the least number of decimal places, which means my final answer has to be here at 0.36. I'm still going to carry that 7 into my next calculation while I convert to grams, but I need to pay attention now that my final answer should have 2 sig figs. So now that I know my number of moles of B2O3, I'm going to go ahead and calculate the number of grams that correlates to. So to convert from moles to grams, I'm going to use molar mass again, but this time I'm going to multiply by the molar mass. Divide by 1 mole. And when you plug that in your calculator, it should be a 2 here. I get an answer 25.56 grams, which I am going to round to 26 grams of B2O3. So I'll have 26 grams of B2O3 left over after this reaction has been completed. Now, In that question, again, I've answered all the questions. What's my limiting reactant? HF. What's my access reactant? B2O3. How much BF3 can I produce? 141 grams. How much access reactant will be left over? 26 grams of B2O3. So, here's just a little list I want to leave you guys with as you continue these calculations to practice. Now, the graphic here is because when you first start doing these problems, you're going to feel like your brain is on fire, possibly exploding, like it's just overheating. And it's okay. You're going to get better at these as you practice more, and it's going to become more second nature for you. Just try not to get discouraged and realize if you follow the process, you will get to the right spot. The questions I want you to think about actively while you're doing stoichiometric problems, especially limiting reactant and access reactant examples. Ask yourself, what's the limiting reactant? How do you determine this? Which reactant is an access? How much access reactant is left over? If you have the information, even if the question doesn't ask it, it's good to still practice and calculate these different answers to the questions because it just gives you more practice throughout the problems. If you're given your experimental or actual yield, what's your percent yield? As long as you know what your desired product is or target product, you can calculate your atom economy. And lastly, with all of these answers in mind, is the reaction worth completing as designed?